Here I'm going to briefly go over some aspects of the second law of thermodynamics, which essentially says that when we calculate an entropy change, in this case we mean a total entropy change, meaning whatever system we're looking at plus the surroundings, the total is greater than or equal to 0. If it's reversible, then delta S total, the system plus the surroundings, is 0. And if it's irreversible, then delta S total must be greater than 0. And of course, any real system is going to be irreversible. So notice in this process, this number could be negative and this number could be positive and at bigger values, so the sum of them is greater than 0. So it's possible for a process to have a negative entropy change. If we looked at some specific cases, an adiabatic and a reversible process. So this means that, of course, there's no heat transfer. Q is 0. And if we look at our definition for the system, dq reversible over T, that's equal to 0. And there's no heat transfer to the surroundings either. So delta S for the surroundings is also equal to 0. If instead we look at an adiabatic irreversible process, delta S of the system must be greater than 0 because delta S of the surroundings is still 0. There's no heat transfer, but the system is irreversible. And if we wanted to calculate the entropy change for the system, we'd have to pick a reversible pathway. So if we're going to from state 1 to state 2 by some irreversible pathway, we want to pick reversible pathway and calculate the entropy, the heat transfer for the reversible process, and therefore the entropy change for the system, since entropy is a state function. So it's important to keep that in mind. Entropy is a state function, so we can pick a pathway to make the calculation easy. Now, if we have an irreversible process where we have just heat transfer to the surroundings, constant temperature, then delta S for the surroundings can be Q over T, where T is absolute temperature, even if Q is irreversible. Another situation we want to look at is if we are running a cycle. And by this we mean we're running a steady state process, running a fluid around continuously in a cycle. Nothing is changing in the system. So if we have some process, we look at any point in the system, nothing's changing. So S is constant at this point. And what this means is for the cycle, then nothing's changing. So delta S for this cycle is 0. Now it can be transferring heat to and from surroundings, and entropy change can be positive for the surroundings, but the actual cycle, there's no entropy change. So finally, let's look at an implication of the second law of thermodynamics. What this says is if we have a process, we're transferring heat from high temperature and we're getting work out, we also have to transfer heat to a low temperature. So, for example, high temperature, low temperature. And so, if we do this, the entropy change is positive for this process. What we cannot do is transfer heat, and we're talking about continuous process, and just get work out. In other words, we cannot convert heat completely to work, because if we're running it as continuous, then the entropy change of our system is 0. Entropy change to the surroundings where we transfer heat from is negative. So the overall entropy change is negative. So this is not possible. And so the second law allows us to predict which processes are possible to do. It doesn't tell us how to do them, but it does allow us to predict if a process is possible. Process would have to satisfy both the first law and the second law.